Today we're going to be looking at some different NMRs, so let's get started with our little 2-propanol. As you can see, we have 3 different peaks, and then we also have 8 hydrogens, so we know that that means that we have some equivalent hydrogens, so let's zoom in to figure out where those are. So we're going to start by color coding this, and so this hydrogen is part of this alcohol, and obviously this alcohol has only 1 hydrogen, so this is going to be our group A. Then let's change colors, and then let's go down here to this hydrogen, and this hydrogen is existing on this bond, and it is the only hydrogen in that bond, so it is again by itself, so that will be group B. And then lastly, we have these 2 H3s that are part of these methyl groups. So what we want to do is show that these are equivalent. So this compound is symmetrical, and these hydrogens are the same distance to here and also to here. So these hydrogens are equivalent, so we're going to label both of these hydrogen groups C, and then that is our 3 different hydrogen groups. So we have group A, which is 1 hydrogen from this alcohol. We have group B, which is this little hydrogen down here, which is also just 1. And then we have our last group, group C, which has 3 plus 3, which is 6 hydrogens. And so that should be all our integrations. And if you look at that, we have our 3 different peaks, each having integrations of 1, 1, and 6. So that lines up very nicely for us. So let's go over to this 6 hydrogen integration peak and double check that this can correspond with our group C. So we're going to write C with a little question mark just because we're pretty sure that's what it is, but we want to double check. So our C hydrogens, we're going to look at this one. His neighbor is right here, and that only has 1 hydrogen. So if we do our n plus 1, we get 2, so it should be a doublet. So let's go back over here and look at that. It is a doublet. So we're going to give a check, and that's awesome. Now we have our 2. I'm actually going to change this to orange to make it more fun and colorful. And I'm going to erase that and give it an exclamation point because we're confident that these hydrogens are causing this peak. Now we're going to go to our other 2 hydrogen, or our other 2 peaks, and try to figure out which one corresponds with A and which one corresponds with B. Let's start with this one over here because it's a multiplet. So we know that that is going to be pretty easy to figure out which one it belongs to because it's going to be a hydrogen that has a lot of hydrogen neighbors. So if we look at our A, we see that, hey, this only has 1 hydrogen neighbor, so it is not going to be our A because the only hydrogen neighbor is down here. So process of elimination, we're going to look at our hydrogen, no, just kidding, it was blue, our hydrogen B to figure out how many neighbors he has, and so he has 3 on this side, 3 on this side, and then this hydrogen, so that's 7 plus 1, which is 8, and I know that that's kind of hard to see, but that is going to end up being our 8, so we can pretty confidently say that this is our B. And then that would be process of elimination. This would make this our A group. But to double check these, we're going to look down at our little table to figure out if our peaks correspond with the proper groups. So let's pay attention to this alcohol. And we see that it can be anywhere from like 0.5 to 5. So scrolling back up to here, our alcohol is observed around 2, so that still checks out for our alcohol, so we can give that a little check. And then we have our little other groups, which are about, well, okay, just kidding. We're going to take another moment to look at this and think about why could this be this far downfield. And I'm going to change this to blue to show that it's the blue. And so we're trying to figure out why this would be downfield. And if you look at where this hydrogen is attached to, it's super close to this oxygen. So this oxygen is leading it to, or this hydrogen is being shielded by this oxygen, so it's shifting it further downfield. And I feel like that's a pretty good way of showing that all of these peaks correspond with these different hydrogen groups. And I feel really good about this NMR. So I'm going to put a little smiley face up here. And then we are going to move on to our second NMR, which is going to be aspirin. So to start with our aspirin, we're going to look to see how many hydrogen groups we can find. So I'm going to actually go in and draw all these little sneaky hydrogens that are around this benzene, so it's easier to see. And then we also have this CH3 right there. Okay, so let's double check. We have 1, 4, 5, 6, 7, 8 hydrogens. So that matches with the formula. So let's now sort these. So we're going to start with our hydrogen in this alcohol again, and then if you look, this whole group right here is a carboxylic acid. So I'm going to take note of that because that is super important. And then I'm actually going to make my little table over here, and I'm going to say that's group A, and it has 1 hydrogen. Alright, so the next most obvious hydrogen group that I'm seeing is these H3s right here. And again, these are not equivalent to anything because they're all by themselves out here and nothing else is connected to anything else like this. So I'm going to make this group B, and that has 3 hydrogens. And now we get to our hydrogens around our little benzene. So first we're going to see if any of these are equivalent, but what we should take note of is that this compound is not symmetrical, so we can't just split this and say that these are equivalent because the connections here are different. So each of these hydrogens is actually going to be its own group. And I forgot to start making my little table, sorry. Okay, so let's count these. We have 1, 2, 3, 4, 5, 6 different hydrogen groups. So then we're going to zoom back out and look at this whole NMR, and we're going to count our peaks. We have 1, 2, 3, 4, and 5. And I bet you're totally panicking right now and being like, what are we going to do? Because we have 6 groups and only 5 peaks, and I also felt similarly until I actually started getting into the analysis of this compound, and then it totally will make sense later. But we're going to actually start with, again, one of the most easy parts of this analysis, which is this little carboxylic acid. So if we look at our little table, very handy, we see that at this 11 ppm, we have, this is only can be the carboxylic acid. So we know that this peak right here corresponds to group A because it's a carboxylic acid. Super easy, super simple. And now we're already 1/6 of the way done with figuring out which groups go with which peaks. So all of these are kind of clumped together, so we're going to do those at the end. But let's move over to this peak over here. So this peak is very tall, but one thing we should take note of is the fact that it is a singlet. So let's change our color again. And let's look at all of our different groups and at how many of these could produce a singlet. So let's just go in order. We have group B. Group B is right here. And our hydrogen, or our neighbor has 0 hydrogens. So that means that our B, the n plus 1, is going to be 1, which is a singlet. So that seems like a pretty good case, but we're going to leave it with a question mark for now. Now we're going to move on to these 3 peaks right here. And all of these peaks are right around the range of 8. So we're going to scroll back down to our handy dandy table and look at 8, and we realize that 8s are, or the range around 8 is usually reserved for aromatic compounds and the hydrogens associated with them. So that means that any of these 4 could go into these 3 peaks. So we're going to do some deep thinking right here, and we're going to notice that this is E and D are both very, very similar. So this, I'm going to change my color again. So E is attached to this carbon, and then this carbon, which is attached to a carboxylic acid. Then on this side, we have our hydrogen, which is attached to this carbon, then this carbon, then this ketone. So these are super, super similar. So these 2 hydrogens are going to have peaks that are super close together. So that could be part of the reason that we only see 3 peaks here when we really want to see 4, because there's overlap between these 2 peaks because they are so similar. So we're going to try to figure out which peak corresponds with which of these, or which group corresponds with each of these peaks. So to do that, we're going to think about downfield shifts. So let's start with, not E, we're going to start with C. So C is attached to pretty close to this ketone. So I'm thinking that this oxygen is going to interact really strongly with this group right here, the C, and that means that it's going to shift it farther downfield. So I'm thinking that this could be C or this could be C. Then I'm going to go over to our F, and F is similar to C in that it's attached to this carbon, which is then attached to this carboxylic acid, which has 2 oxygens. So all of this big carboxylic acid group is going to cause more shielding and therefore more downfield shift. So I can say confidently that this is group D in this peak. So we know that the 2 groups that are overlapping, our our D and E, is going to be this giant tall peak. And then we have all of our groups tentatively assigned to different peaks, but now we're going to dive a little bit further into it. So let's actually go right back into this big group. And we're going to think, why are these multiplet if looking at these hydrogens, they should hypothetically be doublets because all their neighbors only have 1 hydrogen. So this is because, I'm trying to pick a fun color. This is caused by spin-spin coupling. All of these, the electrons interacting around all of these hydrogens are so close together that they kind of get all kind of mixed up, and especially in D and E, where there's a literal overlap in the peaks, it just kind of causes weird stuff to happen, and so all of these end up being multiplet, even though hypothetically it should be doublet. So we're going to go back to our peak for group B. And we're going to double check that this is our, just kidding, sorry. We're going to double check that this makes sense. So this peak is at right around 2.2, And so it is also right on the tail end of this ketone group. So let's scroll back down, look into here, and sure enough, carbonyl compounds are going to exist in this 2 to 3 range. So I feel pretty confident that this is B. So overall, I'm feeling pretty good about this analysis, and I think that we have thoroughly proved that all of these peaks correspond with these different groups. So I'm going to add a little smiley face to this one too. And then I think that we should be good to go. Thanks for watching.